All right. Good morning, everybody. Hope you can hear me. Um, Today, I will talk about computational thinking in economics. And since it's so early in the morning, let's start with some warm-up questions. So let's start like this. Have you heard about this term computational thinking before you came to this talk today? So please raise your arms if you did. So that's most of the people here in the room. Second question, do you think you have a precise definition of what computational thinking actually means? Please raise your arm if you feel do. I don't see any arms here, so maybe we should cover this. Next question, do you think computational thinking is something fundamentally new, innovative, or is it rather something which just got a new fancy name so that we can make presentations about it? Or do you think there is some innovation in this? Please raise your arms if you do. Yeah, some people do. Some people be still sleeping. So last one for the warm-up round. Do you believe that we should invest time and efforts in thinking about creating computational thinking materials? Is this something like good? Or, yeah, okay. Yeah, I see many arms here. So, okay, so I'm trying to sum this up. Many of you have heard about computational thinking. Almost none of you have a really clear definition for it. But we kind of all agree it's maybe something new, but we feel that this is something we should look more into and work on. So this is what I'm going to cover in my presentation today. And so let's start with a couple of definitions. I look for it, and actually there's not so much out there. So today I brought one from Janet Wing, which is the most prominent author in this field, and she says computational thinking is taking an approach to solving problems, designing systems, and understanding human behavior that draws on concepts fundamental to computing. And a little shorter, more compact is what Stephen says, or how Stephen tries to define computational thinking as formulating things with enough clarity and in a systematic enough way that one can tell a computer how to do them. And the last one kind of goes in the same direction. When you look at the definitions, so at least for me, they don't feel very precise or very clear. So I wouldn't disagree with any of those, but I feel they are not exactly pointing to the same thing. And in a sense, they are very broad, or one could say vague. So, for example, in the first one, so this is about solving problems, very abstract term, designing systems, and understanding human behavior. So that's covering a lot of fields and areas. So what exactly is the thing that makes computational thinking different than other approaches? And about the definition from Stephen. So what is it that computational thinking now is different than, for example, programming? Isn't programming something like like formulating things in clear enough that a computer can handle it and do the computations. And what is a computer? Is a human a computer, or is a machine or a server or algorithm a computer? All right, so yeah, so there is no, I think, like commonly accepted definition for this, and so I looked a little deeper in some of the articles and papers about it, and I tried to identify like some terms I found a couple of times, and so what was interesting is like almost all the literature about computational thinking is related to education. So it's nothing like a discipline of computer science or something like this. So it's always about in the context of education. Usually it's defined as a skill, and I think that's actually a good way of thinking about it. I see it as one part or one discipline of problem solving. And so what we need for this like skill, or to develop this skill, is obviously computers. But what are computers? And obviously we need things like engineering thinking, which could be programming, and also things like mathematical thinking. What I found quite a few times is the term abstraction. I think that's a good point, or this is something we should look more into it. And of course, since we are, or since this is about problem solving, it's also about like data and real world applications. Okay, so still there are many terms, and I don't feel like I know exactly what it is, or how to describe it, or how to do it. But still, I have the feeling that it's something useful, or something we should invest more time in. And why is that? So I brought this meme, and since it's a meme, there's some kind of irony involved here. So the problem that many educators or many people identify is that we teach students mainly to learn things by heart, to understand, repeat, and execute patterns. And this is where we spend like most of the time in university or school. And what we don't learn so much is like how to use the methods, how to apply them, when they make sense, and actually how we solve problems using them. So yeah, actually, I mean, this should be like the other way around. So nowadays, like acquiring knowledge should probably not be the highest priority in education, and instead problem solving. So yeah, so this is like this problem solving as we've seen on the last slide. So this is something that computational thinking could achieve. So then in the next step, I'm trying to see what's already out there, to get an idea of like where is this education, this new thing, this computational thinking. And I started looking at very like pure, or trying to look at the most pure forms of literature. And in economics, it's actually like really hard to find a book which is only about economics and not using like math or programming. And you actually have to go back far in time. And I just picked The Wealth of Nations. Every economist will know this book, and dates back to the 18th century. And so I did the same for math and programming. And so these are like the first books or fundamental books, some of the fundamental books in this field. And nowadays what we see is kind of like intersecting of these fields. And so when you look at the intersection of economics and math, what one could call applied math or applied economics, then this is where most of the current like textbooks in economics are. And one example is Halvarian. So every economics student will probably have seen one of his books. And in the intersection between economics and programming, so we find usually books which are motivated like, so here's some economics, and now I explain how you can do the same with a computer, or how you can do the computations with a computer instead of doing it on paper. And the intersection of like math and programming, of course, there are also some examples for these books. And so now, I mean, there's nothing wrong with all these books. So most of them are great for specific purposes. But there's one problem which brings us back to why computational thinking is something relevant to education. And so this is when you look at economics book, usually it assumes that you have some background or taken some classes in math before. Or when you look at a applied economics book, so like programming for economists, something like this, then you will find that some of the like economic concepts are assumed to be there. So what you actually need to do in order to understand like the big picture is like you need to you need to start at some point, and then you are able to go to a next level and look at a new like intersection or new field. And the question is, can we go there more directly, or can we kind of do it more efficiently? So all in one thing. And so this is where I think computational thinking is should be or could be. And this is like really the intersection of all the three fields. Okay, so now like thinking about this, I haven't found any books covering exactly this idea of the intersection of all these fields. So I said, okay, let's try to create something. And here is short preview. So everything you will see in the next minutes is still work in progress. So here we go. So this is one example I tried to create. It's the title is The Tragedy of the Commons. So in economics, we deal with like lots of problems related to the usage and often overusage of public goods. So what's a public good? Something like a lake or a piece of land or a street. So where you cannot or where the access is usually not restricted. And then when many people start to use it, then bad things happen. For example, overfishing. And when you talk to people without a economics background, so you sometimes hear things like, okay, yeah, that's because of the capitalists. They are taking away all the resources, and they're only interested in making profits, and they don't care about the environment and things like this. And then I mean that's fair that some people have this impression, but then one should ask, like, why are people doing this? Are they kind of like stupid in the sense that they are exploiting all the resources without knowing that they are destroying the planet or this public good, and cannot benefit from it in the future? And so this is really somewhat like a very relevant problem in economics. And so here is how I started this. And it all starts with a lake. And I develop like a very, very raw sketch of how this lake works. So I start with an initial population of fish in the lake, and I introduce a reproduction rate, and then we look at, okay, so how is this growing? How is the fish population growing in this lake? And once we have this, now we can see, or we can introduce some natural limits. So the population is not growing to infinity, so there are some boundaries given by nature. And so then we have like a very raw model of how the fish population in the lake works, only by having this limit and the reproduction rate. And now we're going to introduce fishermen. So we start with one fisherman fishing at the lake, and we make some assumptions on the catch and the days this fisherman's working at this lake. And so what we can compute is like a fish harvest, so the amount of fish he takes per year. Okay, so after that, now we can build on this raw model of the lake, and now we see what happens when the fisherman is at the lake. And so we have the fish population and like the harvest, which obviously the fish who are taken out of the lake cannot reproduce. So this has some, or implies some, dynamics. And now only with a few more things we can already build like a very sophisticated model. So now we can kind of like explore this ecological system by having the initial fish endowment and reproduction rate, and the fishermen and the catch as dynamic variables in this simulation here. And the interesting thing is economists would usually look at marginal rates and elasticities and things like this, but with such a like simple model, you can already see that like you can get the intuition. So when you increase the fishermen, the number of fishermen a little bit, so it totally kind of like kills the fish population. So then something like overfishing would happen. Okay, so another really nice I think like intuitive example is when there's 1 million fish at a lake, at a reproduction rate of 5, we can take out 800,000, so 80% per year. And what happens if we just take one more fish per year? So shouldn't make much of a difference. And that's actually true for the first 5 years. But then, as we see, if we keep on doing this after 9 years, the lake is completely empty, overfished. So right. So this first part is really like to understand the ecosystem, and now we keep adding more like economics. So now we have what happens when there are more fishermen. So this is what economists call like a best response. So when there are more fishermen, then it's getting harder to catch fish, and so the decision on how many days per year a fisherman should go fishing then depends on the decisions other fishermen make. Okay, so we introduce this, and then just add a few dollar amounts, prices for fishes, and costs for the boat and gas and stuff. And so we can easily see that when we have one fisherman, then obviously he has the highest profit, and as we have more fishermen, then the profit goes down. And what is interesting here to understand the problem of overfishing is that people wouldn't stop fishing at the moment they make like negative profits. So whenever there are fixed costs involved, this is what economists call it sunk costs in this context, then people would keep fishing even when they make losses at the end of the year. And what happens is that there's no natural regulation, so people tend to overfish a lake. Okay, and now what can we do about it? So there are many ways of government regulations in this respect. So I pointed out like 7 here, and then what economists would do is would look at what is an ideal situation and compare this social optimum to the consequences or like the scenarios of different regulations. And this is actually what I compare at the end. It doesn't look very pretty yet, but at the end it will go like this. So you have 7 different regulation, or you can think of like policies, and then you have certain like cost components, and then you can relatively assign like the size of the cost, and you will see like that these options or these regulation policies are different or can be ordered differently. Okay, so this was the example, and just 10 seconds to wrap this up. It's been like really tough to work on this, so it doesn't look like there's much out there, but I already worked on this for quite a time, and it really takes some time. It's really something like different to create this new type of content. And yeah, here are the 5 takeaways from my work so far. So we should use this abstraction rather than defining like levels of audiences, like this is bachelors or this is like starting levels. So we should focus on real world problems and tell the stories. And like step away from this traditional education approaches. We should not focus on teaching math and teaching methods, computational methods, because the books are already out there. And we should try to fascinate people and don't try to acquire knowledge or findings, and use interactivity as much as possible. Thank you.